Okay, welcome back. I'm going to introduce our new speaker, Yann Thoma. Yann is a professor at the Reconfigurable and Embedded System in the School of Engineering and Management in Vaud. He focuses on FPGA design and verification of hardware accelerators. He currently leads the ReAccess project, where his team and the team in cybersecurity in the same school are partnering with CYSAT to build a new framework for securing SDLS communication based on CPU FPGA platforms. So, thank you, Yann, and I'll let you the stage.
Thank you. So, this is our school. If you like concrete, that's great, actually. And just before starting, we're talking about security today, so just one word about security. For security reasons, I won't be jumping on stage today for obvious reasons. Be sure of that. So I'm going to talk about system-on-chip FPGA. Just one question to start with. Who is aware of what is an FPGA and how it goes? All right, harder question. Who is not really aware of FPGAs? So a lot of abstentions, I guess. All right. So I'm going to present this ReAccess project. In Switzerland, we have something called the InnoSwiss project, where actually the academics are paid by the Swiss government, and the companies have to bring the same amount of work from their employees. And actually, we're doing that with a company that maybe you know, CYSAT. I don't know if you heard about them already. And I'm the guy working on embedded systems. There is another professor working on cryptography, Alexandre Duc, who couldn't be here today, so we'll just be presenting that. That's a 2.5-year project. We're kind of in the middle of it. So I'm going to show you where we are right now and tease about next year, more or less. So just a word about my university. So you know the world. I guess you know where Switzerland is. In Switzerland, there is a French part. Maybe you heard my accent. I don't know. And in this French part, there is the University of Applied Sciences and Arts Western Switzerland. It's basically spread all around this French part. And I'm located in Yverdon-les-Bains with some thermal bath. A nice city. So it's HEIG-VD, that's a nightmare in English. That's the School of Engineering and Management of Canton de Vaud. So the context of the project is basically helping ground satellite communication, where you have to send telecommands to the satellite, getting telemetry with some information coming back from the satellite, from its payload. And the issue is that you could have someone in the middle trying to sniff what's happening or trying to take control of the satellite. Unfortunately, right now, it's usually not really secured, depending on the mission, of course, but not always. And the idea was to work on having some better communication on this. The application of what I'm going to show could be for any kind of missions, could be for commercial ones, for maybe military ones, but I guess they already have some kind of security in military stuff. It's maybe not the case in some ESA missions where you are kind of monitoring the health, the Earth. It could be quite easy, actually, to get information on what's happening on the communication. So the project goal is actually to work not only on software. Up to now, in this room, we heard a lot about software, but not really on hardware. And the idea is to end up with a modular system for software-hardware management of communication, with the idea of, for CYSAT at the end. So the idea of the project is really to build a demonstrator or a prototype, and then to have the company taking care of industrialization of that. And the idea is to offer the clients a framework they could easily integrate into their system, with the idea of being able to share some workload between the CPU and the FPGA. So not everyone raised the hand about the FPGA. So just to know, we usually use CPUs and we program software. The CPU is a general purpose system, quite slow in a sense. On the other side, you have ASIC, so it's really building a device for a specific application. Quite nice, very efficient in terms of power and speed, but it's very costly. And if you made a mistake, you have to start from scratch, and it costs kind of a bit. And so the FPGA are just in the middle. Actually, you are programming hardware instead of programming software. It's like you are creating a new device every time you program that. And so you can take advantage of the parallelism of the hardware. So the idea is to work on partitioning between the FPGA and the CPU, working on key management as well, having the possibility to manage the key within the FPGA or in software. We are also working on asymmetric key crypto system. I'll tell you a bit more about this later on. And over the air, rekeying and reconfiguration, with the idea of exchanging keys while it's working, and also the idea of reconfiguring the FPGA or the software while the satellite is on air. So right now, currently, there is this CCSDS space detailing protocol. If you were here for Anna Barake's presentation an hour ago, you saw that. So we have headers, a payload and trailer, and the idea here with the new part of the standard, this SDLS standard, is to add some security. So you have some security header and tailors, and you would encrypt the payload. That's the idea. And that could be done in software. That's what has been presented previously by Anna. And here we'll see what we can do with hardware. So it comes on that stage in the data link. Actually, you have the packets, and you just have to encrypt and decrypt the packets in a correct way to ensure it's not just free for everyone on air. So what are we proposing in this project? Actually, that's the idea of a modular architecture, where in your satellite payload, you would have a CPU, and you would have an FPGA. That's quite often the case. An FPGA used to process data, pre-process data, and then you have a CPU because it's quite nice to develop software. It's easier, definitely, than working on hardware. And so you have to communicate with both parts of the user application. And usually you have the software taking care of sending the messages and getting back the messages as well. So for doing that, if we add this SDLS part with the encryption, decryption, so you would need to encrypt and decrypt within the CPU as a software library. You also need to have a key management part. We saw that in a previous presentation, and also the security associations, which is more or less what key should I use for what channel and what algorithm should I use for what channel. And so that's, I think, usually what is happening right now. So the idea of our framework is that you could say, okay, I want to leave more space to the CPU, and I want to take advantage of the FPGA to accelerate processing. And so you could embed the encryption, decryption engine within the FPGA, quite transparently, that's the idea. But you could also say, okay, I want the key management to be in the FPGA as well, because then it would be a bit faster and more efficient in that way. We would keep the security association right here because it's a bit complex and a lot of memory required, so it's not that nice to have it on hardware right now. But what could be done is to say, okay, instead of having the CPU taking care of the communication, then you could say you have some specialized hardware ready to do that, and you could go through the FPGA for this. It means if you really want to reach very high speed, that would be better to handle all the sending and receiving in that part of the FPGA. So basically, the idea of the framework is really to say, you have all these options, and actually you could use some conditional synthesis for the FPGA development. Say, okay, I want this or not, I want this or not, I want this or not. And then you can choose, and the software would adapt directly, and you don't really have to take care of all that. That should be kind of automized in a way. In terms of encryption, right now we've been kind of playing with AES 256 and ASCON 128. And actually, this core could be replaced by something else. I'll show you what we've been doing with that until now. One thing as well is that we were talking about NewSpace here. So you could have a system like this that would be radiation aware or ready for radiations, or not. So in NewSpace, you could use kind of a standard FPGA, which is not ready for that. And so the idea is that you could use some triplication at some stages just to say, okay, that part is really critical, I don't want to lose anything. That would be the case, for example, for the key management. But you could say that for the crypto engine, if there is an issue, you have an SEU arriving, maybe you would have an issue with an encryption. That's not a big deal. You lose a packet. That's part of the process. It's quite usual to lose some data. And if it really goes wrong, you could reconfigure the system if required. And so we are working on different parts as well to identify what is critical, what is not really critical in this. We've been implementing that on a real hardware. So for that, we didn't use a rad-hard FPGA system. We used a standard Zinc system on chip that's from Xilinx with this board. And actually on this board, you have an FPGA with some, so that's for the ones who know the FPGA, what you would find inside. There is also inside a CPU, a double-core ARM Cortex-A9. And that's the idea that on the same device, you have the CPU and the logic you can reprogram. And for that, so we used two different crypto engines. Actually, the idea of the project was not to develop the crypto engine in itself, so we used two ones available as open source, with the idea that that's a proof of concept, and then we could change that with another one if required. So I'm going to show you some numbers on this. So the design we did implement is we have the CPU and the software running, and we have just the crypto engine. There is just one core able to encrypt and decrypt. All right. And actually, that's what we ended up with the ASCON version. AES, that's a small version of AES. In the larger version of AES, you see the different numbers in terms of that's basically the resource you are using for the system. And what we see is that for the FPGA we've been using, that's a very low cost one, so quite small in a sense. And for that, we are basically using 25% of the space for the ASCON and 70% for the AES. And this one is red because actually you couldn't fit it because that's too huge for that small FPGA. In terms of speed, so here we have numbers with the hypothesis of running at 50 megahertz, but I know we are able to run at better frequency than this. And so here what we see that this ASCON is a bit slower than AES. And I will show you in this slide the data rate we should be able to attain. And we see that with AES, the large version, we can end up with quite good, like 600 megabytes per second encryption, which is not that bad, actually. And but the previous, if I go back here, that's just the encryption in itself. So if you just have the core, that's what you could expect. The issue is that you have to send the data from your CPU up to the FPGA. Then it takes time. And with that, we have a drop in data rate. So we are below 90 megabytes per second for this large AES one, which is kind of reasonable considering what we've been implementing on this. For the decryption, it's more or less the same numbers. I won't spend time on this. You see the same kind of thing. The interesting part is that the two AES are quite close together for the decryption, which is a difference compared to encryption. We've been comparing software as well, because the idea is to accelerate things on hardware. So here what you see is kind of interesting. We have the encryption time for software and for the hardware, and we see that the hardware is worse. And that's not exactly what we did expect. So it's twice the numbers of hardware. And actually, this is because that's really a work in progress. So in 2 weeks, I have better numbers. I asked the organizers to shift CYSAT, but they didn't agree. So we still have to wait 2 weeks. And that's just because of the transfer of data. Actually, you see here this last line, that's just the time to send and get data back. And that's actually most of the time really encrypting and decrypting that's very fast. And that's because we just implemented a rapid prototype with just sending data one at a time, so 30 bits at a time. And that's too slow, actually. And so the idea is really to take advantage of burst by sending data all at once. And these are numbers that are actually calculated. We couldn't implement that yet. And if we have some burst, then we see that the numbers right here are definitely better than what we would have in software. And that's really something I'm sure we'll achieve. There is no reason why it shouldn't be done like that. And if we use the burst, as we see here on the right, that would be on the green, the data rate we should be able to attain with bursting all the data compared to what we have in software right here. What we see as well is in terms of data rate, obviously the bigger the packets, the better the system will be because the burst will be very fast and then the encryption is fast by itself. So it should really help in the future. What we can do as well, I told you, is to add sender and receiver blocks with the idea of if you don't want to have the CPU taking care of the communication in itself, it could come from a fee here where basically you would have the FPGA directly accessing the physical part of the communication. And for that, I just want to show you what would be the data path for this. So basically the data would be sent here, sent through the crypto core, and then go back there. It goes to this because there are some data to manage strangely on the packet. And the same for receiving. We can use the same core. So you cannot receive and send at the same time for sure. But usually if you want to be very fast, it would be in one direction, more or less. What can be done as well is to have some user application within the FPGA and directly accessing the system to send the data. So that's something that we know there is a company that is currently interested in having a 2 gigabit per second sending of data from the system. And that would be the way to go because we don't want to go back to the CPU and then go back to the FPGA to send something. It would be too slow. And that will be the way of going to have something quite efficient. So here just numbers about what is the cost of having a sender receiver on the FPGA. Basically, you had you had half of an ASCON core to have the sender receiver on the FPGA. So that's just a graph. Within the project, we also developed a test framework with CYSAT, actually, where actually you can run the ground system. There is the embedded system part, so that's C code. So, and we have a manager for this that is communicating with both thanks to gRPC and eRPC protocols. And so you can run different commands on the ground, on the satellite, and to test the system. What we did add is the idea that, okay, you could use that with just the software part of the system, or having the FPGA system in simulation. So for those that are using or doing FPGA development, you have to test it as any system. And actually, CocoTB, that's one of the framework which is written in Python. So actually, you write a test bench in Python, and with Python, you can do whatever you want. And so it was quite easy to interface Python with the embedded system. And so you can run a test with your C ground, C space, and the FPGA device on the same one. And what I didn't show on this, in that we could directly link the FPGA to this part if we want to go through the FPGA instead of going through the CPU. Just 2 words on cybersecurity, because I'm not the expert one, but just about what we are working right now on, or the cyber experts are working on, is adding asymmetry, because the current standard SDLS, it's with symmetric keys. And the team is working on asymmetric cryptography. They have identified the way to go for this. It won't be post-quantum yet. So within the project, we will stay with standard, which should be a kind of a Diffie-Hellman system. But if we have a framework that is ready for asymmetric keys, it means that the key management should be ready for that as well. So it will be ready for post-quantum. Just, I think the issue would be the size if we want to have this encryption on the FPGA. Maybe post-quantum could be an issue. One thing as well that the team is thinking about is the idea of having an evil launcher. Actually, if you prepare your satellite with symmetric keys, so you have the keys on your satellite, you give that to the company responsible for launching the satellite, and maybe you trust them, maybe no, and that could be an issue. So having asymmetric cryptography would help to mitigate this risk, because you could be able to regenerate new keys on the fly and be sure that these new keys are not compromised. But that's an ongoing work. So the next step of the project is working on this over-the-air rekeying and over-the-air reconfiguration. So the idea that you could reconfigure the FPGA if you want to change your protocol at some stage or change the algorithm. You could send your bit stream maybe in 1 or 2 turns around the Earth. I don't know, but that's something that could be done. And one last thing is this asymmetric cryptography, which is not part of the standard. That's the idea of maybe proposing to amend the standard with this. So that would be for the next year. So that's a work in progress. Stay tuned. The idea is to be back next year with the cryptography expert as well, and ready to show you the final steps of that project. Thanks to the team, and I'm ready for the questions. Thank you.
Thank you, Yann, for the interesting talk. Do we have any question in the room? Oh, perfect.
You were talking about encryption and decryption, but are you also doing authentication?
That would be the responsibility of the software. We are not doing that in the FPGA right now.
I can answer that, and yes, it will be responsible to call AES also for doing authentication. Any other question? Oh, on the back, perfect.
Just one question about the keys. Where are they actually stored on the board?
All right, so yeah. So the key, they could be in software, and the software could send the key, but we developed a key manager. Yeah, I didn't show that actually. So we have a key manager that can be responsible for taking care of the keys, up to 100 keys. And the idea is that the keys could be outside. So you could have a special memory, safer memory, I would say. And then the key manager within the FPGA taking care of checking that everything goes well, if required. For the first prototype, we had the keys within the FPGA, but the idea is really we have an interface and that could be outside.
Okay, any other question? Okay.
Thank you for the presentation. Is the software and the FPGA implementation is compliant to each other in case we want to use one of the system as a redundant of the other system? Are the software version and the hardware version are compliant to each other?
Yeah, that's the idea at the end. So at the end of the project, the idea is that as a user, you could say, okay, I want the key management right here, I want the encryption right there, and then it should compile as is.
And the software version is a closed source compiled binary. What is the plan? Do you expect a similar for the FPGA version, for the IP?
So that would be for CYSAT. I'm the one developing things for fun as an academics, but that's CYSAT that will have to choose what they do with that then.
Okay, thank you.
Actually, just to response a little bit, as we spoiled the few sessions before, SatLink, at least part of it, is going to be open source. So, well, if there are any more questions, thank you again for the great presentation.
Thank you very much. Thank you.